Hello. Hi guys, good morning. Welcome back to a new video. In this, we're gonna see prime numbers masterclass. This is our not famous prime, but this video is because we saw a problem in contest which was of prime numbers, and also we have been seeing lately a bit prime number related stuff. After this video, any problem if it says na prime, after that you will be able to solve it. In this we will discuss that what are prime numbers and the problems related to prime numbers also I'll give you in the end with the videos also. Then we will see how to check if a number is prime. Again, we will go on the very standard brute force approach to the optimum approach. We will also see how we can find the prime factors of a number. Again, brute force approach, optimum approach we will see. Then we will go on and check how to know and how to compute what all prime numbers we have in a range, which means from 1 to n, L to R, or whatsoever range. In that we will learn about Sieve of Eratosthenes. Don't spell that name from me, like don't ask to spell the name from me. But in that, mostly people just tell you what it is happening, but they never tell you what is the time complexity. And if they tell, then they never tell that firstly, if let's say in an exam, or let's say if you forget that I don't remember how I actually reached onto this complexity, then I'll give you a pseudo complexity which will actually help you, and we'll also prove that for everything. We'll also see that how this is derived, and then I'll also show you that how that is proved. So no worries, everything will be covered. And then we will see the improvised version of that Sieve of Eratosthenes, which you will actually be using in your final and all the codes, which means you will use that as a snippet forever. Now ultimately we will see that how we can find the prime numbers in a range. What I mean by range is, Aryan, you have discussed the range right here, right? No, so this range above what I have discussed is a normal range. But let's say I ask you have to find the prime numbers in a range from 10 raised power 12 to 10 raised power 15. Let's say this is the range. Then I ask you to find the prime numbers. Then what you will do? Will you apply sieve? No, you cannot. So in that cases we will use segmented sieve. So that is, I will also teach what is segmented sieve, and ultimately we will see practice problems again, which will have the video solution of them. And also I will give some problems which you can do by yourself as a practice, again from all the platforms which you can see. Now let's start off the video. First of all, what are prime numbers? So basically, as you might have learned in your first, second, third standards, basically a number n is called prime if it is only divisible by either 1 or the number itself. Then the number is prime, which I can also infer the same thing as a number is called as prime if it is not divisible by any number from 2 to n minus 1. It is not divisible by any number from 2 to n minus 1. Then I can simply say, bro, it is a prime number. So Aryan, but that sounds good, but in maths or basically in programming, how this will be helpful for me? So basically in any problem whatsoever, as you can see in this problem also, I have some prime. In any problem with the word prime comes in, apart from doing a modulo with the largest prime number, if anything comes in any problem comes which has prime number related any concept, then this video is the full stop solution for you for any prime problem. So which means we can just have, if you want to check a prime number, if you want to generate prime numbers, if you want to compare numbers and tell if they're prime or not, if you want to operate on some prime numbers and do some operations on top of it, which means getting the factor, getting the prime factor, all that stuff we will actually see in this video. Cool. So just start off with how to check if even a number is prime or not. As we saw the actual definition, that we can simply go and try that number n, it should not be divisible by any number from 2 to n minus 1. Then I can simply say that specific number is a prime number. So I will do the exact same thing. Brute force is nothing but exactly doing what the problem says. So, and also to just check if a number n is prime or not, it is also called as a primality test. I don't know why, but it is called as that. So I just simply go on and check if this number n is prime or not. So I'll simply go on, and for sure number 1 is never a prime number. So I just go and start off again. I go and start off from 2. and I will keep on going up till less than n, up till less than n, and then I'll simply check, bro. If n mod I, which means the number, original number n, if it is divisible by any number between 2 to n minus 1, then it is not a prime. So simply return a false here itself. Else, if we tried on everything, it did not return as false, then I can simply say it is actually a true, which means it is a prime. So you can simply see I am iterating to check if a number n is prime or not. I am iterating on for every number 1, 2, 3, which means 2, 3, 4, 5 up till n minus 1. So it is nothing but O of n complexity. Space is O of 1 because we are not using any extra space. But if I ask you, you want to improvise that. Now, when I ask you, you have to improvise, which means you have to make the complexity better than n. What can be better? Either it can be root n or it can be log n, right? Now, let's figure out something, some pattern we have to figure out. And again, remember this pattern because this pattern is very important in maths concept and number theory, and it is very highly used in the later part of the video. In all the optimizations, this pattern will for sure be used. So please consider this as a very serious part. So we can easily see that, okay, if my n is 36, so I can simply mark the divisors of n as, okay, 1, 2, 3, 4, 6, 9, 12, 18, 36. One common pattern I can see is they form a pair. Okay, 1 and 36 multiplied will form a 36. Okay, 2 and 18 form a pair. 3 and 12 form a pair. 4 and 9 form a pair. Okay, if the number is actually a perfect square, then the mid number, it may not form a pair, but still I have the numbers in the form of a pair. Okay, what if the number is 12? Then again 1, 12, 2, 6, 3, 4. Again, if the number is actually a prime number, then still 1, 11. They will still form a pair, which means the divisor will still form a pair. So what we can infer from this, okay, that we saw that all the numbers, which means that, okay, for a number n, all the divisors will form a pair for it. Now, what it tells us is that we don't require to go and check the entire n. See what we were doing earlier. What we were doing, we are going on and trying for all the n up till the n, super n. We are trying. Now I am saying, bro, why do you need to try? What you were trying? You were trying just if some number I is a divisor. If some number I is a divisor of my n, then you will simply return a false. That is what you were trying, right? So now I am saying, you know one thing, that you can only check the divisor in the left half of the portion, which means up till root n. You can only check the divisors in this portion because for sure, if you find any divisor in this left half, you will for sure will have a divisor in the right half, corresponding divisor in the right half. So you only need to check in one half, which is the left half, or you can also go and check in the right half. And if you find, okay, oh bro, if I find something which divides, then for sure this would have also done the exact same thing. So you can see the divisors are equal in both left and right, and they're actually complement of each other. So if one divides, if let's say 2 divides something, then for sure 18 will also divide my 36. So I need to only check if 2 divides or not. That's it. So that's the reason I'll only do one thing. I added and I only went up till root n, which means I will go up till root n only. Usually it's a good practice to not write a square root of n, although you can also write the square root of n. That will also completely work for us. So what we did was we went up till the square root of n because we know we only need to check the left half, which means the up till root n we will check all the divisors. If that is that, which means n mod I is 0, bro, you have already found, and there is no need to go further to check if something divides or not, because if in the left part if nothing divides, then for sure in the right part also nothing will divide. And that's how I optimize my time to O of root n. Now, you might say, Aryan, O of n, O of root n are still more or less same. Bro, they are not. How? O of n, for n is 126, it is 1e6. O of root n, it is 1e3. You saw how big difference it is. It is actually. So, actually optimizing to O of root n is actually a very big achievement. Now, okay, we saw one thing, that how to check if the number is prime or not. Then other parallel thing comes in, that how will you find the prime factors of a number, which means what is the prime factor? Firstly, prime factor simply says if a number n is 100, so I will divide that number as a multiplication of its prime factors, which means I'll say, okay, prime factor, I'll simply say, okay, it's 2 and 5, but 2 is occurring twice. 2 is occurring twice. 5 is occurring also twice. And multiplication of this will give me a number 100. That is the reason I can simply say that, okay, prime factors of my number 100 are 2 with a count of 2, 5 with a count of 2. That is the prime factor which I can return or I want to return. Now, why is this useful and all that stuff? It is usually asked for you to iterate or basically to work on the prime factors of a number. Then you will have to generate the prime factors, and then it can also be asked. You will see in many code forces around, problem C and problem B are mostly on maths or number theory concept, and the prime is the favorite part for them. So that is the reason it's very important to know how to generate the prime factors. Now we'll use the exact same funda as what we saw above. Why? To check if a number is prime or not, that firstly I need to generate the prime factors of a number n. So I will ask for a number n and I will try to generate the prime factors of that number. How I will do it? I'll simply go and try. Okay, bro, try simply from 2 to up till equal to n. I'll just go and simply have a try that if n mod I is a 0, again have it a less than, or you can also have it equal, because if you want to generate prime factors of a number, you can simply see that what all you need in the output itself. Now n mod I is equal to 0, which means that number I is dividing my n. Now if something is dividing my n, so keep on dividing that number by n until it is not divisible by n, which means, okay, if I had a number n as 100, now my I first time came as 2, so okay, 2 divides 100. Now 2 is a prime number, I know. Now keep on dividing this number 100 by 2 so that you can get the count of how many times my number 2 divides this number 100. Okay, I'll say 100 by 2, 50. 50 by 2, 25. Now I cannot divide. So count of 2, which means count of times that my 2 divided by n will be my 2 itself, which is the count of that. So if something divides Aryan, but how will you make sure that you will only and only try for the prime numbers, because you want the prime factors, right? So how will you make sure that, okay, you will only try for the prime numbers? Bro, if I am dividing, let's say if I try for number 2, if I divide that number n by 2 as much as possible, which means that no matter what in future, this n will not have any multiplication of 2, which means any factor of 2, it will not have it. And if something is not having it for sure, which means no 4, no 6, no 8, no 10, no any other number which is not a prime number will not be there because of 2. Again, next time, let's say I try for 3, I'll try. If 3 is divisible by this number n, remaining number n, then I'll simply try and keep on dividing. So what I did was, if something n mod I is 0, then you also have to get the count. Because if you remember, prime factor is 2, which is I, but also get the count, which is how many times that prime factor divides my number. So while my n mod I is equal to 0, simply keep on dividing that number by I and simply keep on incrementing your count. Ultimately, when you have done the entire division, which means that the entire n is exhaustive of the number I, simply push back the I, which is the prime factor, and the count of that prime factor. Now because of this fact, you will go and try for all the numbers, right? And then you can ultimately keep on pushing back in your answer. So your answer will have a vector of pair of n comma int. Now this pair is nothing but first key is nothing but the prime factor itself, and the next is the count, how many times that prime factor is coming in your picture. And with this fact, you will be very good to go. So you saw that what is happening. What is the time complexity of this problem? Time is nothing but you are going on to all the numbers, so it will be n. Okay, n. But you will see that you are actually also going on and trying and dividing that number again and again by I. Now I is nothing but, okay, as you saw, it will come only inside for I equal to 2, I equal to 3. It may be, it can I equal to 5, I equal to 7, and so on and so forth. So even if I take I equal to 2, and then imagine that, because again smallest I is 2, so roughly I can say no, that it is nothing but n by 2. So every time is number being divisible by 2, so n by 2, n by 2, n by 2, n by 2. So this operation is nothing but log into the base 2 operation. But okay, right now this is nothing but for just I equal to, for I equal to 3 it will be much less, for I equal to 5 it is much less. So much less seems like much less. Cool. So because of that, I can simply say no, that okay, O of n for this fact and O of log n for this fact. So time complexity will be O of n log n and space is O of 1. But again, remember, make sure time will be much lesser than O of n log n, because log n I considering only, okay, log into the base 2, but it will be log into the base 2, log into the base 3, log into the base 5. So it will keep on reducing for every n piece, which means it will be log n to the base 2 plus log n to the base 3 plus log n to the base 5 and so on and so forth. And roughly I can say it can be n times, but not n times, because you can see 4 is missing, my 6 will be missing, so on and so forth. So that is the upper bound, which is n log n. And this also is a very important thing which will be very helpful in future also. Future as in the upcoming part of the video. Now, coming on that, how will you improvise that exact same funda of root n? We will simply go and try up till the root n. But Aryan, okay, that was the divisors which you were checking. These are the prime factors which we are checking. How are they linked to each other? Bro, simply, we will work on observation. What? Let's say if we take a random number 15. Now, we know that we have to improvise that, which means we will try on up till the root n time. Root n is 4. So we are saying that I will go and try on all the prime factors less than equal to root n. So Aryan, are you saying that you will have all the prime factors of a number less than equal to root n? No, bro. It is very obviously visible to you. How? For the number 15, prime factor only 3 is there, which is less than equal to root n. 1 is still outside my root n. How will you find that? Same way for this, let's say less than equal to root 28. You have only one prime factor which is less than root 28. Other is 7, which is outside this range. How will you find that? So you got one thing. Okay, Aryan, that root n thing doesn't seem good to me. Okay, I will go and try for all. The values and check if that is a factor less than equal to my root n. But I can also see I can still have a prime factor more than my root n. What will you say about that? I'll say, bro, there's a very slight catch. What? That there will be only one prime factor which is more than your root n, and that is you can simply grab. How? Because let's say if I take very beginning 15, I'll take the root n, which is roughly less than equal to 4. Now I know that I will go on and try again. Although it will be less than 4, which means it will be 3, but still, let's say even if I take a 4, no worries, but yeah, okay, for your simplicity, let's take a 3 floor value. I'll go and try for simple all the values which are less than equal to my root n. So I'll try for first value will be a 2. I'll try for 2. 15 more 2, not divisible. Okay, 15 more 3, oh, it's divisible. If something is divisible, then you saw one thing, keep on dividing that until it is divisible. Okay, 15 more 3 is divisible, which means 15 is divisible by 3. Keep on dividing that. Bro, I cannot divide it further because it can only be divisible one time. Okay, if it can be divisible only one time, so 3 is a prime factor with a count of 1. Simply push that in your answer. Okay, now try for a 4. Okay, 4 was not required because your root n was 3 itself. Okay, no worries. So your loop will end right here. But now I am saying your n is still remaining as 5. Your n is still remaining as 5. Now my claim is that this n is actually your prime number. This n is actually your prime number, and it is the only prime number. Aryan, okay, we want to find the prime factors. Okay, so you are saying, Aryan, you are saying right now that this 5 is a prime factor, and you are also saying that this prime factor will have a frequency of 1. Is it? But how are you so sure of that? Because very simple thing. I know that this number which is remaining, it is more than my root n. Because if it would have been less than my root n, then it would have covered here itself, which means my prime factor which is remaining, it is less than my root n. Sorry, it is more than my root n. If it would have been less, it would have been covered here itself. Now it is more. Okay, if something is more, right, and I am saying it is for sure a prime number. Oh, how can you say that is a prime number? Because it was not divisible by any of the smaller number. And to make it okay, if you say it's actually a number which is not a prime, so okay, if this is a number, then for it to be not a prime, I should multiply it with something to make my final number n. Now you saw that, okay, multiply it with something to make a final number n. Multiply with something which is higher than root n. Oh, which means let's imagine this as root n. I have to multiply with something which is higher than root n to actually make it a number n. That's impossible. That's not possible at all. So that is the reason whatsoever will be remaining for us, that again, that should be more than 1. That will be the prime number for us, again with the frequency of 1. So I can simply say one thing, that whatsoever, I'll keep on trying up till the root n, I'll keep on trying, and after that whatsoever is remaining will be a prime factor with a count of 1. So I mean exactly same, is just that after my loop is completed, I know if something is remaining and it is more than 1, so that will also be my prime factor with a count of 1, and that I can also push back in my vector, which is the answer of your prime factors and their corresponding count. Thus you have optimized your code to run at the time of root n into log n, right? And yeah, space use is actually O of 1 itself. Now comes the most interesting part, which is the part 3 of the video, in which you have to check the prime numbers in a range, which means I am asking you one basic question. Bro, right now you just checked for one number n if that is prime or not. Now I am asking you, in the range of numbers from 1 to n, give me all the prime numbers. Give me, again, range can be anything, but I'm asking you in the range from 1 to n, give me all the prime numbers. Now you will go and ask, bro, if I go and try my normal brute force approach, which I have learned, and maybe if I try the optimum approach, so I'll go and try for all the number n. Let's say, okay, 1, 2, 3. I'll go and try for all the numbers n. For every number, I'll go and check if that is a prime number or not. In the optimal approach, which we have seen, will give us a root n time. So it will ultimately take O of n root n, which is very high for us. If we consider n is actually 1e7, it is very high. So now our task is to optimize that. How will we optimize that? In that comes is Sieve of Eratosthenes. Now in that we will see that how it actually works. So now let's come back and see. We had n root n. We have to optimize it. Now what is the better optimization which we can have? We can have a O of n log n. Now how? Again, you are just backtracking that how you actually can think of that what could have happened in the Sieve of Eratosthenes algorithm. So we went on back and saw that, okay, I have to make a n log n. Now what if I bifurcated n log n? What visibly it seems like is, or it actually is, that okay, I'll try for all the numbers n. Now maybe by some magic I can figure out that if a number is prime or not in a log n time. Although here I was saying to figure out if a number is prime or not, the most optimal approach was a root n, but now I'm imagining maybe if I can figure out in log n time, which is for sure not feasible, because in the beginning itself we had seen the most optimal approach to figure out if a number is prime or not in the root n time. So this cannot be optimized, but still I have to improvise it, which means still I have to get to a O of n log n. So okay, now rather than jumping on to and deriving backwards from the complexity to the actual approach, we will see, okay, let us see and figure out what optimal, or basically what better we can do if we have to go and find out all the numbers in 1 to n to check if that is prime or not. So we'll simply go backwards. We'll simply go forward. That we'll just try to optimize it as much as possible. How? We'll simply have all the numbers. Let's say example, we had all the numbers up to 16, and we have to figure out in all the numbers if something is prime or not. So what I will do is, by default I will say, bro, by default I'll say one thing. Let's imagine all the numbers are prime. Aryan, but how did you think of that? Bro, if you remembered one fact previously in this specific approach, I was going and trying for all the numbers, right? And when I was going and trying for all the numbers, let's say I tried for a number, if you had gone and remembered, I was trying for number 2. Now as soon as I tried for number 2, I kept on dividing that number 100 by 2. Because of that, what happened? Now that number 100 had no more factor of 2, which means that if I just imagine, okay, 2, then 4, then 6, then 8. So 4, 6, 8, 10, 12, all of them became redundant after I did a simple continuous division by a number 2. So I can reversely think of the same thing and can do a continuous multiplication, which means let's in the very beginning imagine all the numbers are prime. So I will keep a variable, I'll keep a vector to to just say is prime. I will say, okay, that specific ith number, okay, I is 2, 3, 4, 5, 6, and so on and so forth. By default, I marked all of them as prime. Now, and please make sure that 0 and 1 are not prime, so you can just by default put them as false. Now, you went on the first number. You know it is prime because it's a first number, right? You will know it is prime. So, you know number 2 is prime. But you also know all the multiples of 2 or all the multiples of 2 will never be prime. So I know one thing. Oh, I can just say 4, 6, 8, 10, 12, 14, 16. All of them will not be prime. So if I am at a number 2, I will go and mark all of them as not prime. Now Aryan, okay, which means that you are going on and trying for a number n, and on that you are jumping on again. I don't know right now what can be the complexity of this algorithm, but I'm just trying to improvise that, okay? I don't have to function on that 4, on that 6. In future, I will not have to function on my 4. Okay, 4 is gone, 4 is dead, 6 is dead, 8 is dead. So I never have to repeat this entire jumping mechanism later on in future because I know they are already dead. Okay, now Aryan, but how does jump happen? Is this jump happening? Okay, right now you are at the ith number, which is 2. So this number j, which you are jumping at, is the j. You are jumping at a plus I, which I can see. Okay, it's a plus I. Yeah, okay, that is true. That okay, I'm jumping at an interval of I itself. Maybe I can optimize that also. Let's see. So next time comes as 3. Okay, next time number came as 3. Now this is also prime. This is also prime because it has not been marked as not prime so far. But if you saw in the above operation, when I was at 2, I marked all the numbers 4, 6, 8, 10 as not prime. So this prime variable will become false for all of them. Now, when I was at 3, I will again go and say, okay, bro, by this fact, I can simply say, okay, number 6 will not be a prime, number 9 will not be a prime, and number 12, number 15, and so on and so forth. But you saw one thing. I did not jump to 6. I jumped directly to 9 itself. Because you saw the 6 was already covered by my 2. So although you can jump to 6 and then have a quick check, but then you can have a bit improvisation that the first jump which you can take directly to a I square. I directly went on to I square, and then I kept on incrementing my I. Okay, I was at I equal to 3. I directly jumped on to 9 and had a first check rather than 6. Although I could have tried the jump of 6, it would have been more or less same, but still a bit improvisation which you can remember, that you can just do a directly jump to a I square, and then you can just keep on incrementing by I. Okay, increment by 3, and mark all of them as prime as false. But now you will say, Aryan, in this case you went on to 12 again and again. Can't you improvise that? No, bro, it is not always possible to improvise everything. And see, this I square jump also is a very small improvisation, very small, negligible. Even if you want, you can still try on with plus I, which means you can also do a jump with, okay, plus I, which means plus 3. That is also exactly same, right? Cool. Now we went on to 4. So 4 is already marked as not prime. So simply move on. It is not even a prime number, so simply move on and try for next number. Okay, I am at 5. Simply same fact. Okay, 5. Keep on marking the multiple of 5 as not prime. So I'll go on to 25. Oh, but 25 is even outside my limit, so for sure leave it. I go on to 6. Already marked as not prime. Go on to 7. Already marked as not prime. 7. It's a prime number. So I can just simply go on and try for its multiple, which is 49, which is next number. But you will simply see that it is also out of my bound. So with this, you saw one thing. Okay, Aryan, I don't know what could be the complexity of this. No worries, I am here for you. But you saw one thing, that we did a very high optimization, and I can visually show you the optimization which you have done. Firstly, in the worst to worst case, if you think of, you are going on to all the n numbers, right? Now this jumping says, okay, jumping is in the smallest jump is of 2 itself. if the smallest jump is of 2, oh, Aryan, smallest jump is of 2. So are you saying that the jump is my, like, I will have to go and try for a jump of 2, so I'm just doing a n like n into 2, like n plus I, so it's kind of roughly n by 2 itself, right? So this jump is n by n, like jump of 2, so n, I am just trying for two elements, so it seems like a O of n by 2. Aryan, okay, you are saying that you will try for O of n and then O of n by 2 jump. So worst case, it feels like O of n square, isn't it? That is a catch. It is not O of n square. Now, we will see that how is the complexity of this algorithm, which is the most trickiest part. Firstly, but before that, let's have a quick glance of the code, which we will write exactly same of what we saw above. Firstly, we will mark everything. Again, my main task was to find the numbers from 1 to n, or I can say roughly from 2 to n, if those numbers were prime or not. So by default, my 0 and 1 numbers are by default not prime, so mark them as false, and rest of them from 2 to n, mark them as by default true. For sure, we will assume all of them are prime in the very beginning. Now I will go on and try on for all the numbers from 2 to n, and then keep on incrementing that. So as I showed you, I'll go and try for all the numbers, which means 2, 3, 4, 5, 6, and so on and so forth. I'll try for all the numbers. But the next inner loop, which I saw you, which I showed you, that okay, it will go on and try in this entire array only when it is prime itself. So 2 was prime, so it was going and jumping on to all the multiples, like plus I, plus I, plus I, when my number I was prime itself. It was prime, it was jumping. It was not prime, so it never jumped, it never went inside. So I have to write the same thing, that if the number is prime, then I will do jumping, and jumping I will start by default from I into I. Although you can start off your jumping from I plus I also. It's up to you. It's up to you, totally up to you. But for a better improvisation, you can start jumping from I into I. Again, I'm saying you can start in from I plus I also, because you know that you were at I, and you can just simply do a plus I of jump, which means you can jump a 3. So it is I plus I. Next time you will just do a plus I jump. So okay, it's I plus I plus I, and this you will keep on performing this plus I jump. You will keep on performing. But I'm saying in the very beginning, rather than doing a plus I jump, you directly go on and reach to a I into I. That can be your starting point. That is a small improvisation which you can have. Now, cool. So what we did was simple, that I start from my I into I, as you can see, and I kept on incrementing my jump by plus I, plus I, plus I, plus I, and then up till it is less than or equal to n. And whatsoever is the multiple, basically whatsoever is, because of my I marked those j as false, because if I is prime, then those j's cannot be prime. Cool. So those are marked as false, and ultimately returning my entire is prime vector. So this is prime vector will say as true or false for all the numbers, which means 2, 3, 4, 5, 6, 7 are the indexes, and that is true, 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 false, true, false, true. So this true indicates that this index I is a prime or not. This is what this array will return. Now comes the most interesting part. Its complexity is O of n log into log n. And space is O of n, because you saw that you are actually making a O of n space right here. Now, how is this O of n log of log n? I have heard of Aryan, I have heard of O of n square, O of n log n. How is O of n log n? How is that? So for that, I will show you firstly what is happening at every index. So at I equal to 2, it is kind of going on to the entire array up to the length of n. Again, I'm bifurcating that, and make sure you listen to it very carefully. So at I equal to 2, right, it is going on and trying for, okay, the entire n roughly, right, entire n, it is going and trying on entire n, which means it is doing a jump of 2. So I know one thing for sure, that it will roughly take O of n by 2 times. Jump of 2. So it is kind of roughly iterating on the n by 2 elements, right? This inner loop I'm talking about is inner loop for the specific I value. Okay, when the next time I increased, let's say I is 3, it will go and do a n by 3 jump in the worst case. Okay, let's imagine n by 3 jump. Again, it is for this specific I. Make sure next time when I equal to 4, it is for sure not a prime number, so it will never jump. Okay, so nothing, no n, nothing. If I equal to 5, it will do a n by 5 jump, Now, if I just show you what is happening, just have a smaller picture. What is happening? I equal to 3, 4, oh, never, 5. Now, if I ask you what will happen for 6, 6 also it will never go because it is not a prime. So I can easily infer one thing from this entire table is, which I have derived right now, is that I am roughly saying for I equal to, I am going to n by 2 jumps. I equal to 3, n by 3 jumps. I equal to 4, I didn't go anywhere. I equal to 5, n by 5 jumps. I equal to 6, I'll not go. I equal to 7, n by 7 jumps, and so on and so forth up till n by p, where p is another prime number. So ultimately what you have to find is what is the summation of this, where p is your prime number. So I have to find the n by p, where p is the prime number less than equal to my n, which is 2, 3, 5 up till less than equal to my n. What is the p? I have to find this summation. This is a math problem. But now you will say, Aryan, I'm not that good in maths. Can you give me a, like, okay, I just want to have an estimate. Even for me, okay, you are saying the complexity, where is this gone? You are saying the complexity is n log of log n, right? I can say now roughly the upper bound of this n log of log n is O of n log n. So even if I can right now prove the complexity is O of n log n, I can tell my teacher, okay, ma'am, the complexity is n log n. And if you want to go more deeper, the actual complexity is, it is O of n into log n into n into log of log n. So, okay, for the folks who are just interested, okay, just give me an estimate complexity, which can actually be very less. So I can say that, okay, I can roughly say, well, see what this sequence is missing. This sequence is missing O of n by 4, O of n by 6, and so on and so forth. So I added those numbers which are for sure not in my actual code, right? So I'm kind of increasing my complexity. So if I just add these numbers right here, so I can simply get my n out. It will become a simple harmonic progression. And the sum of this harmonic progression, again, if you don't know what is harmonic progression, please go and like read this. I'll simply zoom it up. It's a simple harmonic progression, and the sum of that is log n. Thus, I can simply say it is O of n log n, which is this part is log n, this is n, it is O of n log n. So I can simply say the upper bound complexity of this entire code of Sieve which we wrote will be upper bound. I'm saying again, upper bound will be O of n log n, and for sure O of n log n also will work for us. But now let's see what is the actual complexity. As we saw, it is just that we have the sum of all the prime numbers. This is nothing but 1. Again, this was never there, so it is the sum of 1 by 2, 1 by 3, 1 by 5, 1 by 7, and so on and so forth. So it is 1 by prime number, 1 by next prime number, and so on and so forth. So now I have to go and find the sum of that. For that, again, although it is an integral question, which means integration is involved for that, so for the folks who are very much interested, you can see that it will something becomes like this, where you can just simply have these two facts. With these two facts, I will have a quick glance at these two facts. So this says that the number of prime numbers less than or equal to n is approximately n by log n. So I can say n by log n, n by log, again, I'm not writing ln, I'm writing again, ln is base e, but I'm writing log so as to make it different by n. So I'm saying n by log nth prime number is n, right? This I can say. So I can say first prime number is n. Again, this is all rough estimate because you can see is approximately all rough estimate. So it will be n into log n by n. So first prime number roughly will be nothing but log n. So kth prime number will roughly be k into log k. So I know the kth prime number will roughly be k into log k. So if I have to say that, I can simply say 1 by p. I can simply say p. The kth prime number will be k into log k. Now if this have to improve, which means if I have to solve this portion, it will become a simple integral question, which means integration from 2 to n by ln n, 1 by k ln k. Now integration, if you want to know, good. If you don't want to know, it will simply land back to ln of n. And that's how I can simply say my time complexity of this n by p summation for all the, where p is all the prime numbers, it will be n into ln of n, which means n log of n. And that's how, again, if you want to read the more entire proof, please go and pause this and read the proof, and the entire proof is written in this book itself. So now we have derived the complexity of this entire sieve will be nothing but O of n, O of n log of log n. Cool. Now, but Aryan, in the beginning intro, you showed us that you can also improvise the sieve. Is that true? Yeah, because you saw we'll use the exact same funda of root n. If you remembered, since we'll use the same funda of root n. How? That I know that I will not have nothing after root n. Everything will be before root n, right? All the numbers are in, but you told now that you can have a prime number after root n also, bro. I by default have assumed all the numbers as prime or not. So my numbers which are less than my root n will help me to actually make other numbers which are more than root n as not prime. So what I did was I am only iterating on up till the root n, and this will help me again. Don't confuse it. I am not saying that I am not going after root n to know and find my prime number. I have by default assumed I have all the numbers as prime. So assume that. Now I am going on iterating on all the numbers less than my root n, and because of those numbers, I will go and mark all the numbers after root n also as not prime. So, and because we know one fact, because all the numbers which have divisors will also have divisors in the right part also. So I'll simply go and try for up till root n, and then if that is prime, simply go and mark all the other numbers which are j as not prime. So the only change between above code and this code is nothing but this specific change. That's it. Now, as soon as people see this code, they just jump on and say, Aryan, in the above code, you showed us the complexity of this code, which you showed above, where it is just simply going on I. It is nothing but O of n into log of n. This is what you showed. Now you reduce the you reduced it, so the complexity is O of root n log of log n. No, bro, no. That is the reason I expanded the entire I portion. I expanded that. It is, if you improvise that, it will not be O of root n into log of log n. It will still be roughly O of n into log of log n itself, which means more precisely it will be O of n into log of root n. That will be the actual time complexity of this, which is, again, roughly you can say it is n of log of n, or you can also say roughly as n of log of n. N log n, you can say roughly. That C will give you the complexity again. But please use this specific code, because it will unnecessarily not go into the right root n portion, which is actually much more optimal, right? But still, on paper, the complexity is still the same, but you have to always use this specific code, mark this as a snippet, and use this code always. Now, but Aryan, I didn't understand why it is not O of root n. Bro, simply, if you go and look back, what I showed you is the n portion in my n log of log n, it came in from the inner loop. Inner loop brought in n by 2. Inner loop brought in n by 3. Inner loop brought in n O of 1, which means it never went inside. Inner loop brought in O of n by 5. So inner loop is actually bringing in this n time, not the outer loop. Outer loop is giving me the p factor. If you remember, the p factor was because of the I equal to 2, I equal to 3, which is the outer loop. So now you're actually reducing this p factor and not the n factor. Thus, the complexity is nothing but O of n into log of root n. That is the reason. Again, space is O of n, simple sieve. Now, this is what you have seen for the simple Sieve of Eratosthenes. But there's a slight improvisation, as in there's a slight follow-up for this. That, okay, this sieve you saw, and you, if you remembered, you actually made a vector of size n. Okay, and then you went on to all the numbers from 2 to n. Okay, still great. But let's say if I ask you, bro, you have to go and find me out all the prime numbers from 10 to the power 12 to 10 to the power 16 or 10 to the power 14. Let's say if I ask you this. If I ask you this, then will you make, you know your L is this, R is this, and R is roughly n for you. So will you make a vector of 1e14? Impossible. Cannot make. And the same way, will you go up till 1e14? Impossible. Cannot. Then what to do? What to do in this case? This is called as segmented sieve. Now, what we do in this case is that And see, firstly figure out what is this case actually. I'm not saying that I am going and trying on all the numbers from 1 to 10 to the power 14. Nah, I am saying 10 to the power 12 to this 10 to the power 14. That is my actual range. What is different in this range? What is so special in this range? So special in this range is that the range length is small. Range length is similar to actual range, which is, if you had remembered, 1 to n, we know the complexity was O of n log of log n. Now for now, let's imagine it is O of n log n for your simplicity, and space was O of n. So if I can see that, okay, 1e7 can work in your code forces and stuff, 1e7 will work, but in your Leetcode 1e6 will work. I don't know why Leetcode have very constructive time constraints, but yeah, in Leetcode 1e6, but yeah, still it's the complexity is still the same. Don't worry on that part. But yeah, you can simply imagine 1e7 will work. Right now, I'm not saying that, okay, your n becomes 1e14, so you should also be able to do 1e14. Nah, this is the most optimal you can ever think of. Now I am saying the range length is small, which means the range length is also incurring elements like this, which means I can say 1e9 to 1e, let's say 12. I know the range length is 1e4, which means I have 1e4 elements in this, but the range length maximum element, this L comma R, this R is very high. So in that kind of scenarios, I will use segmented sieve. What? So my range length is small, which is within 1e7, but my R is very large, which means let's say 1e15, 1e13, like so on and so forth, which is beyond your integer. In that case, what we need to do? We will actually say that, okay, if I have a range L comma R and my range length is small, which means my R minus L plus 1, which is the range length, it is small, which is around 1e7, again maximum 1e7, then I can simply, but my R is large, then I can simply use my segmented sieve. Hey, Aryan, what is the segmented sieve? See, segmented sieve just says that, bro, generate all the, again, the same fact come in, root n, root r, generate all the prime numbers less than equal to root r, and then from that generated prime numbers, please mark all the composite numbers. Composite is not a prime number. Mark all the composite numbers in range L to R as not prime. So I'll do the same thing. Again, that is the reason I have specifically mentioned that this root R thing is very important to understand how the numbers work before root R and after root R. What are the numbers? What's the specialty about those numbers which are before root n or root r? Cool. Now, for a quick example, we will see that, okay, if I ask you for the range L to R, where L is 40 and R is 50, then you know one thing for sure, that I will, again, by this fact, I will go and generate all the prime numbers which is less than my root R. So I will, again, Aryan which means that my number n, it can be very high, but let's imagine your n is 1e15, which means your R, let's say your R is 1e15. Still, your n, like root R, will be 1e7. So still you can find all the prime numbers in the range from 1 to 1e7. That's right. That's correct. So I can simply find the prime numbers in range 1 to 1e7. So when I will do that, I will simply, again, for this fact, my n was 50. My R was 50. So I can just 50, like root of 57. So I'll go and I'll apply the sieve in the range from 1 to root R, and then I'll generate all the prime numbers in that range. So I applied the sieve in this range. Again, sieve, exact same optimal approach we'll apply, and then we can simply say I've generated all the prime numbers in the range 2 to root R. When this is done, I will use those numbers to mark what all numbers are composite in this range L to R. I'll simply say 2. Okay, 2, I'll simply go and say, okay, 40, 42, 44, 46, 48, 50. Mark all of them as false, which means I'll simply take an array is prime by the name is prime, and that I'll mark by default as true. All of them are true, and I'll keep on marking all the multiples of these prime numbers as false in that range. So I for my number 2, I marked all of them as not a prime number. Same way, let's say if I am at 3, I'll again go and say, okay, mark all of the multiples of this number in that range L to R as not prime. Okay, mark my number, as you can see, I marked 45 as not prime. Same for 5, I can mark I can mark anything, but you can see your 45 is already marked as your false, so no worries. For number 7, I will mark for 49 as not a prime. So whatsoever is remaining in this range, you can see 41, 43 and 47 is remaining. So these three numbers are the prime numbers. Now the code is exactly very simple, very short and simple. We'll use the exact same snippet of R prime to go and find out the prime numbers in the range of 2 to root R. So my actual question was to get the prime numbers in the range L to R. But I will call my simple Sieve function and will ask, bro, can you please give me the prime numbers in the range 1 to root R? So I'll go and ask up till root R. Root R, give me the prime numbers. So he will give me the prime numbers, right? Again, this gives us, again, remember, this gives us the array. This array is a Boolean array where the indexes is okay 1, 2, 3, 4, 5, 6, 7 and so on and so forth. So the value true indicates that the index is prime or not. Remember that fact, how the output is generated. It's totally up to you that how I want to generate the output, but yeah, this is how we are generating the output. So now this is the existing from 1 to root n. What is the prime numbers in this range? This I will get it from this prime. But for the current answer, which means from L to R, I have to go and find out the numbers are prime or not, right? So I will go and make an array of size R minus L plus 1. Now in this, I'll again go and apply the same exact same sieve logic. As you will see, exact same sieve logic. How? Simply go and start from the 2 up till the root R, because I know I will use this portion to actually make this entire portion from L to R as composite. So I know I will go on from this portion, which is this specific portion, entire this portion I'll go on and we'll try to make L to R as composite. So if this specific ith number is not a prime number, bro, simply continue. Don't have to make L to R as anything because it's not a prime, right? If it is a prime number, then I will go and say again the exact same thing. I into I plus I less than equal to n. Simple. I into I less than equal to like plus I and less than equal to your R. But here's a small catch. What is small catch? Aryan, you also put something here. What is this? So if you remember, this I into I says, okay, I will try and say I into I again for let's say for example for this 2, I into I will be 4. Is this even logical to make 4 as your not prime? No, right? It is not logical. You should actually make your 40 as a not prime number, right? So you will have to say, okay, I should be more than my L. It should be more than my L. But again, more than L, but the first multiple of your ith number. It should be more than L, but it should be first multiple of your I. So I'll say, okay, either it should be maximum, then I into I, which I was doing earlier, but also maybe if I into I is small, then first number which is more than my L, but is a multiple of I into I. I'll get that number, and I will actually start off from that number itself. So this is a small change which you have to do from your sieve to a simple segmented sieve. And again, and if that number j is not a prime number, so mark your j minus L as false. Again, if you had seen, your array is R minus L plus 1. So if I take an array from 40 to 50, so array is L to R. So you will make a simple array of size 0 to R minus L plus 1 is the size. Now R is nothing but 50 minus 40 plus 1, which is 11. So you will mark from 0 to 0, 1, 2 up till your number 10. You will simply marking that up. Now if I ask you, you have to populate j, your current element j. Let's say your number element, let's say element your j is 41. So 41, let's say if it is, oh, let's say 42. Let's say 42 is actually not a prime number. So in this array, what you will mark? You will simply go and mark, okay, 42 is not a prime number. No worries, bro. No worries. Simply mark your index 2 as your false. This is false. This 2 represents 42 now, because I know that this LR is a very big range, like very big numbers, but a small range, which means it can be 1e12, 1e14. So it can be a very high number. I cannot make an array of this high number. I can map it to a smaller numbers. So I'll simply do the exact same thing. It is L, it is R. If this is my jth element, I'll simply say j minus L. Simply mark that in my array as false. So I'll mark my J minus L as false. Now, if you had seen that, then you will also see that if your L is 1, which means if your L right here is 1, so you have to also mark that 0 as false. So if I just mark as, if I simply ask you, if your L would have been 1, which is if I would have asked you 1 to 50, right? So this would have made your array and said, bro, simply make an array and say 0, 1 up till so on and so forth, r minus L plus 1, which is 50 minus 1 plus 1. Length is, sorry, 50 minus 1 plus 1, length is 50. So I will be simply making a length of my 50. So last index will be 49 itself. Oh, 49. So that will be my entire length. So I know last index is 49. So, okay, 0, 1, 2, up to so on and so forth. So if I'm marking this as 50, okay, 50, if R is 50, then I will say 50 minus 1 is 49. So mark that as false or true, whatever you want to mark. But if your 1 will never be counted, because 1 is not a prime number, so it will never be going inside this I equal 2, because it starts off from I equal 2 itself. So by default, your true will be marked for 1, for your this index 0, which should have been the corresponding value of 1, that would have already been marked as true. So if something is 1, it cannot be prime, right? Please mark that as false, because you can see it never goes starting off with 1, it goes from 2 itself, because we check from 2 itself. So if your L is 1, please mark the index 0 as a false, where is gone, as a false, and I can simply mark that, and with that I can simply return the prime. So you will see that if I just give you a dry run of how this, if I give you an example of how this actually is called, so you can simply call in from 40 to 50, give me the prime numbers, so you'll get the answer. This answer array is again, remember, it's a range from 0 to R minus L, right? So I know if I have to get the answer from L to R, simply add a L. So I get the answer from L to R. So I simply added a L, I added simply a L in the current I. Again, answer of I is true, which means that ith prime number, that number I is actually a prime number, and I have to give me the prime number in this range L to R. So please simply add a L in that prime number to actually get the actual prime number. So with that, I can get my actual numbers as 41, 43, 47, and that is the answer in the range 40 to 50. Cool. And again, the complexity is same as that of sieve, so it will be R minus L plus 1 log of R, and this is for the standard sieve, which we are calling in from the, see, this is the L to R, and this is the root R sieve, which we are calling from this specific sieve. Cool. Now comes the last portion, which is the problems which you can try off. So you can try all these problems. It is the mixture of everything, like code forces, Podge, UVA, like everything. It is a mixture of. Now in Leetcode, if you want to watch a video, you can watch this specific video right on YouTube, 2601 by Aryan Mittal, Leetcode 2601 by Aryan Mittal. You'll get the video, or you can write this entire copy pasting to Leetcode 2601 prime subtraction operation by Aryan Mittal. You'll get this video. And as I showed you in the very beginning, that today's contest included this specific video, as I showed you. So this specific problem of prime number, so that also we will be discussing in the next part. So yeah, you can also find this specific video. I know that this video was this video is the entire thing which you need to know about prime numbers. Everything you need to know about the prime numbers. So now you are very good with prime numbers. Cool. Bye bye. Take care.